2 billion tons of waste accumulate annually, with glass constituting nearly 20% of the total volume. Why does this material demand such special attention? At first glance, it seems like simple trash. But in reality, a single bottle can remain in a landfill for over 1 million years without decomposing. But this is just the beginning. Unlike other materials, glass can be recycled forever without losing any of its quality. Messy, sharp shards enter the system to be reborn as clean, shiny bottles. One can notice the continuous stream of glass moving on rubber belts inside one of the world's largest recycling factories. Hundreds of tons of material are brought back to life here every day. The process is only gaining momentum. The secrets of the most sustainable material on Earth rely on precise engineering to unlock. The operation proceeds to the sorting phase. 10 to 20 cents is the precise financial value assigned to every single empty bottle returned by consumers in this automated system. Instead of ending up as useless waste, the container instantly turns into a valuable asset. This small refund drives the entire recycling economy in many European countries. Consumers simply place the empty beer or soda bottle into the machine for immediate processing. But this is just the beginning. Why is this source separation so critical compared to regular household trash? To the casual observer, glass appears easy to retrieve from any general waste bin. But without this specific isolation, sorting becomes a costly engineering nightmare due to contamination from other household refuse. The reverse vending machine scans the object and sorts it into the correct category within milliseconds. This infrastructure provides factories with a stream of glass that is chemically clean and consistent. While Europe has fully integrated this solution, the United States still relies on a patchwork of local systems. The process is only gaining momentum. Specialized collection companies dispatch trucks when the machines signal they are full. Large plastic bins, each holding thousands of empty glass bottles, require forklifts for loading onto the decks. One can notice how the heavy transport suspension compresses under the increasing mass. A single full-size truck accommodates between 20,000 and 30,000 bottles in one coordinated trip. This aggregate volume equals approximately 10 to 12 tons of raw silicate material. Piles loaded with glass make their way from supermarkets and collection points to the central recycling plant. Each bin is packed tightly to maximize transport efficiency. The drivers back the heavy vehicles into the massive storage bay with precision. They release the load, sending a cascade of bottles tumbling down into the intake zone. At first glance, these piles look like chaotic waste, but in reality, they represent the essential starting point of the recovery chain. Dust slowly settles as the deafening noise of colliding glass fades away. It is visible how the industrial ground fills with colorful mountains of greens, browns, and clears. The shards sparkle under the facility lights, stacking together in huge mounds. The raw material now waits to be cleaned and crushed. Tens of tons of waste glass accumulate in towering piles before the recycling process begins. Why does the cycle start with such aggressive, heavy machinery? Glass seems to require delicate handling, but to process such immense volumes, massive loaders must scoop up huge loads with their buckets and carry them across the yard. With a thunderous crash, the material is finally dumped into the plant's feed hopper, sending a chaotic cascade of shards down the steel chute. Instantly, the steel conveyor starts moving, carrying the stream of glass mixed with dirt and sand deep into the facility. The first stop is the vibrating screen, where powerful mechanical shakes separate out dust, grit, and tiny particles. At first glance, it seems obvious that machines should handle the entire flow, but in reality, larger contaminants require human eyes. Along the conveyor, workers stand ready, carefully pulling out paper, plastics, and other debris. One can notice how their hands move with practiced rhythm to clear the line. This blend of mechanical screening and manual labor produces a cleaner batch of material, preparing it for the next step in the recycling journey. Do you know what is still hiding in that pile of broken glass? The flow moves rapidly. The answer is bottle caps. Luckily, most of them are made of metal, allowing easy removal via a high-powered magnetic separator. The principle is simple. The strong magnetic field grabs the bits of steel while the glass keeps moving down the conveyor. Thanks to this step, the glass is now about 80% clean. But this is just the beginning. Once most of the contaminants have been removed, the glass moves on to the next crucial step. To ensure uniformity, larger pieces are fed into a hammer mill, a massive machine with high-speed rotating hammers that smash the glass until only tiny fragments remain. Any pieces that are still too big are automatically detected and sent back through the mill until they reach the right size. This makes sure the entire glass stream is uniform with no stragglers slipping through. The process creates cullet, fine sparkling glass particles that look almost like man-made sand. Because it is broken down so small, cullet melts much faster in the furnace, saving up to 40% of the energy compared to raw materials. After that, the cullet is carried to a powerful suction system, where it is blasted with a strong stream of air. It gets more complex further on. This airflow strips away and blows off any leftover label fragments, leaving the glass even cleaner. One can notice the cullet moving into the optical sorting system, the most precise step in the entire process. Glass cascades down like a shimmering waterfall past the sensors. Laser sensors continuously scan each tiny fragment to detect its color and composition. The moment brown, green, or stray ceramic shards are identified, the system instantly fires a precise puff of air, shooting it into a separate stream. Tens of thousands of pieces are processed every single minute. This ensures that the color is sorted with perfect accuracy, as the slightest mix of the wrong shade ruins quality. From here, the sorted material continues moving along the conveyor belt. Consequently, the tiny glass particles are directed into separate storage areas, each divided by color. There, they gradually pile up into massive stockpiles, waiting to be transformed into brand new glass bottles without haste. 20 to 70% is the proportion of recycled glass, or cullet, that makes up the foundation of every new batch waiting to be transformed. Pure silica sand provides the essential clarity, while soda ash, or sodium carbonate, reduces the melting temperature to save power across the line. Limestone joins the mix to strengthen the final structure and ensure stability. At first glance, using cullet seems optional compared to fresh ingredients, but it allows the melt to flow faster and cuts energy use by up to 40%. But the composition involves more than just these basics. Manufacturers introduce dolomite, alumina, or metal oxides to adjust the color and physical properties. Why is the addition of recycled cullet strictly calculated before the melt? The mix undergoes precise blending to guarantee uniformity before reaching the furnace. Adding just 10% more cullet reduces overall energy consumption by about 3%, significantly lowering carbon dioxide emissions. One can notice how the blended material enters a massive gas furnace where temperatures rise to about 1,750 degrees Celsius. The mixture begins to glow, surpassing the heat of molten lava from a volcano. Workers inside the facility must wear heavy fireproof suits and protective gloves to operate near the equipment. The surrounding heat reaches nearly 3,000 degrees, creating an environment that is almost unbearable without protection. Carefully monitoring the process prevents any deviation in the melt. It does not end at this stage. The mouth of each crucible is sealed to maintain thermal intensity and control the melting process. At first glance, the sand seems to melt instantly, but in reality, the transformation requires 24 hours to turn the grains into a substance flowing thick like lava. The brilliant glow at the bottom of the furnace reveals liquid glass. a dense, shining mass that has reached the perfect temperature and viscosity. For the next 5 hours, the material remains molten. This allows any remaining gases to escape, ensuring the highest purity in the final material. Because liquid glass requires a precise vessel to take shape, mold creation becomes the priority. Engineers use advanced computer-aided design software to calculate every line, dimension, and thickness with high precision. Molds are manufactured from cast iron or alloy steel capable of withstanding temperatures of up to about 1,400 degrees. These forms are prepared to receive the melt and shape it from the inside. Transition to the next level. The completed molds are installed into the double blow production line, which serves as one of the most widely used and reliable methods for shaping hollow products like food jars. The process begins by dropping molten gobs, cut from a continuous stream, into the initial blank mold. One can notice the intense orange glow of the glass, which reaches temperatures of around 1,011 degrees Celsius. A jet of compressed air blows from above, pushing the material against the walls to form a bubble-like structure known as a parascent. The glowing glass is gently transferred to the final mold situated just a few inches away on the line. A second burst of compressed air shoots directly into the center, stretching the softened material until it presses tightly against every contour. This ensures the bottle takes its full shape in just a matter of seconds. Everything only gets more complicated. But behind the scenes, every valve and sensor synchronizes with incredible accuracy. The timing is calibrated down to 1,000th of a second. It is visible how the newly released bottles radiate a deep red heat, shimmering in the dark like glowing metal rods. Such precise control allows the facility to manufacture hundreds of thousands of nearly identical units per day. Robotic arms move with seamless programmed precision to lift each bottle and place it onto the conveyor belt. The scene unfolds in calm silence without a hint of haste. The process is only gaining momentum. The belt guides the containers through a long yellow tunnel where the temperature lowers little by little. This cooling stage may last several minutes, and sometimes even stretch to tens of minutes. Quick cooling would shatter the glass, but this gradual process allows the material to settle safely. Therefore, an array of optical sensors and high-speed cameras examines each unit in real time to detect defects like cracks, bubbles, or scratches. Any bottle showing the slightest warp is immediately flagged and pulled off the line. The system rotates each item to inspect the mouth with mechanical probes and sensors. Only containers that pass this strict check are allowed to move forward. And this is not the limit. Robotic systems organize thousands of bottles with ease. The palletizing section takes charge of the batch for accuracy and uniformity. One can notice how a clamp mechanism with suction cups lowers to grip a full row and sets it carefully onto the layer. To protect against impact during handling and shipping, a sheet is placed between each level. An automated wrapper secures the stack in film and tags it with a code that corresponds to its production batch. The glass pallets move into storage, neatly stacked and ready to travel across the globe to serve in daily life. Millions of glass containers navigate the complex production line every single day to hold the world's most iconic soda. Why do automated nozzles fill each unit down to the exact milliliter? The conveyor moves at a breakneck pace, making such accuracy seem physically impossible to the naked eye. This precision is necessary because carbon dioxide gas is injected simultaneously to lock in the signature fizz. Before this filling stage, high-pressure hot water and steam blast the interior surfaces to eliminate any microscopic dust or bacteria. But this is just the beginning of the journey. The bottles head straight to the capping station immediately after filling. At first glance, capping seems like a simple mechanical impact, but in reality, it is a critical safety barrier. Crown caps are pressed onto the rims by precision machines to ensure the contents remain secure. High-precision sensors integrated into the line inspect every cap for tightness to prevent even the smallest leaks. One can notice how the bottles continue gliding smoothly along the conveyor belt like a programmed assembly. A high-speed camera system checks for cracks, overfilling, or misapplied labels to ensure absolute quality. The items move through each stage of the line with a steady, precise rhythm, eventually reaching the water spray station, where a high-pressure jet of cold water targets the neck of each bottle. Everything only gets more complicated. Therefore, the perfectly sealed containers are packed into cartons to complete the assembly process. Pallets loaded with the finished product move into cold storage, awaiting the final leg of their trip. They are ready to be shipped to millions of stores worldwide, from small roadside shops to luxury hotels. The production cycle concludes here, leaving the beverage ready for distribution. Zero impurities remain in the glass containers leaving the production line. The material has transitioned from jagged shards into a uniform product. One can notice how light passes through the walls without refraction. At first glance, this seems simple, but in reality, it restores full value to the material. The cycle reaches its logical conclusion here, but the utility continues. Why is this transformation technically significant? The bottles look identical to virgin glass. However, using cullet drastically reduces the furnace energy consumption. It is visible how automated systems align the vessels for packaging. The technology turns waste into a chemically pure resource. This process guarantees the preservation of raw materials. Thus, the broken shards have regained their function. The finished product enters the supply chain,